Welcome back from lunch. So this will be a quite technical presentation. I hope you don't fall asleep with all the food. So now, today I would like to talk about code reuse attacks for the web. And this is a joint project with two of my colleagues, with Christoph Kotovic and Eduardo Vela, and myself. And in the last few months, we developed a technique that is very similar to return to libc attacks in the binary world for the web. And the idea of this new attack technique is to bypass cross-site scripting mitigation techniques. And this is today's agenda. So in the beginning, I would like to give a very short introduction to XSS and XSS mitigations. I assume that most people know what XSS is and have seen XSSs in the past, but I still will give a short introduction. Then we will talk about the concept of a script gadget. That's a way how we can bypass the XSS mitigations. And we found these gadgets, and we were wondering how prevalent are they in real-world applications. So we conducted two different studies. We conducted a qualitative manual study on popular JavaScript libraries and frameworks to find these gadgets, and we conducted an automated study at scale of the Alexa top 5,000 websites to see how many gadgets we can find in real-world applications. And what we saw there is that these gadgets that allow bypassing of these mitigations are prevalent in almost all frameworks and all applications that we see. And basically, it shows us that XSS mitigations are maybe the wrong way of moving forward and protecting against cross-site scripting. And that's why we are proposing a new way of defending against cross-site scripting. And we do so, we focus on DOM XSS for this part because solving all of cross-site scripting is pretty difficult. And I will talk about this in the end of the presentation, and then we will also have a summary and conclusion. But let's start at the beginning at what actually cross-site scripting. So here I have a very simple example. I think all of you should have seen one of those examples. It's a very simple cross-site scripting. It's a reflected one. It just prints out a greeting message. And in the usual case, a user would type in his name into the get parameter, and then the greeting message would be rendered by the browser. However, what's the problem here is that the username is printed in this greeting message without any encoding. So an attacker could just name himself script alert1, and then this PHP script would run. It would insert the script alert1 here. This would be sent to the browser, and the browser would see a script tag and say, hey, there's a script tag, so I probably should just execute it. The server is telling me to do that. And the problem with this attack is that here the alert is just a placeholder for what you can do. And basically you can do, with a cross-site scripting attack, you can do anything a user can do. So what you do is you craft a payload in JavaScript, then you send a link to your victim, the victim clicks on it, and then this payload would execute in the authentication context of this person that clicked on the link. And then you can do anything that this user can do. If this is an administrator of the application, you can probably administer the app, maybe delete the database or read the database, send some data away. If this is a user that is maybe a message board poster, you can post messages in his name. You can maybe read his private messages, and so on and so forth. And it's pretty bad. And in theory, cross-site scripting is a solved problem. So I think if you talk to academia, they would say, yeah, we know exactly how to do this. You put some contextual encoding here, the right encoding function, and then the problem is solved. And however, theory is not the practice. In practice, that's different. And here we see a graph from Google's bug bounty program. And this is basically the payouts that we pay for bugs. And what we see here is that we pay about 60% of all the payouts that we give out to researchers are spent on cross-site scripting. And what we see is that cross-site scripting is everywhere. And we have guidelines, we have trainings, to mention the point that I was trying to make before, but that doesn't help. So developers still do mistakes, they still introduce bugs, and that's why we have 60% of the bugs to be cross-site scripting. And in the recent years, a lot of XSS mitigations were introduced. So we have ideas how to prevent the bugs, but we often see, hey, bugs are present and we cannot really prevent their existence. So let's not try to focus on the bugs, but focus on the attacks. And that's what an XSS mitigation actually does. So the idea of an XSS mitigation is to block the attack instead of preventing the vulnerability. And here I have a very simple scheme. This is a web application. So it's rendered in a browser, it has a server, and we see a cross-site scripting injection. We have a parameter called injection, and it's reflected in the page. And in this scheme, I would like to explain how XSS mitigations work and what kind of different XSS mitigations we have. So the first XSS mitigation that probably came up were web application firewalls. They are pretty simple. So they sit in the server and they just look at all the requests that come into the server. And then they throw a bunch of rules or regular expressions or whatever onto these requests. And then they are trying to find malicious injections. So they look at this and they find maybe, oh, there's a script tag in the request. There should never be a script tag in a request. So I better block this request. So web application firewalls try to detect malicious markup and then block requests. Another XSS mitigation that works a little bit differently are XSS filters. And one of the first XSS filters that was introduced was the no-script XSS filter. And it's kind of works in the same way as a firewall, but instead of sitting on the server, it sits in the browser. And it does exactly the same things. It protects you as a user. It looks at all the URLs that leave your browser, throws a bunch of rules or regular expressions on it, and sees, oh, there's a malicious script or an onload event handler or so I better block this. And then it just removes the part of the request that contains the malicious markup. And the idea is then it's not getting injected and you're not getting exploited. Then there was an evolution of cross-site scripting filters. So the problem with no-script is that it has a huge number of false positives because it just uses these matching rules. And the next generation of cross-site scripting filters were the IE cross-site scripting filter and the Chrome cross-site scripting filter. They work in slightly different ways, but how they work is basically that they first look at the request, they try to detect whether there is malicious markup in the request, and then they wait for the response from the server. And before executing the response, they check whether this malicious markup that they detected in the request is also contained within the response. And if that's the case, they try to either remove the payload or block the full request. They're different modes. And then recently, we have a new XSS mitigation theme, and that's the content security policy. And it works a bit different, but from a theoretical point of view, it's basically the same. So what CSP does is that it tries to detect legitimate markup that is supposed to be in the page and non-legitimate markup that is injected. And then it will just execute the legitimate one and block the malicious one. And it has different ways of determining whether something is malicious or legitimate. And it has a whitelisting mode where you can say everything from example.org is a trusted script and everything from evil.com is not a trusted script. It has a nonce-based mode where you can say this script carries a unique nonce that the attacker cannot know. That's it. That's why it's legitimate. Or there is no nonce, so it's malicious. And it also has a hash-based mode, but that's not too important here. But again, the principle is detect malicious stuff, detect legitimate stuff, block the malicious stuff, and leave the legitimate stuff in place. And then we have another mitigation techniques, which are HTML sanitizers. So sometimes you're in a situation where you have a user-provided string and you want to render it as HTML. Maybe you want to allow the user to make something bold or italics or whatever. So you want to allow injection of HTML, but you don't want to allow malicious HTML injection. And a sanitizer basically takes a string and it removes all the malicious parts from it. And then you have the assumption is you have a safe string that you can render without XSS. And if we look at this, all of these mitigations work in the same way. They try to detect legitimate stuff and try to block malicious stuff. And what we looked at is whether this basic assumptions of all these mechanisms is true and is in a modern application that is built with modern JavaScript frameworks. And the very short answer is it's not true. It's wrong. And in the next 30 to 40 minutes, I will explain why it's wrong. So let's look at how a modern web application works. So here we see a very basic HTML and JavaScript block that you could find in any UI component library. So here we have a button and a piece of HTML and a couple of data attributes here. And basically, this could be, for example, a UI library where you have button elements. And then usually you have accompanying JavaScript code. And this accompanying JavaScript code tries to add behavior to the button. It might have hover effects and it defines what happens when you click and so on. And in this case, this is a very stripped down case. So here we just mark that this div element is a button, and then we have a data text attribute. And we say, okay, this is the text that should be rendered on the button once it's in the page. It's very simple, but there could be way more functionality here. And then we just say in the script, we just select this button, why this marker over here. And then we say, okay, let's render the data text attribute in this button so that the user can display. So now and what happens then, this code gets executed, and then the button gets rendered, the text is on the button, and so on and so forth. It's very simple. So now there's a question for the audience. So does anyone see a security problem in this code with XSS mitigations in mind? Yes, exactly. That's exactly the case. And I have this example here. So the security issue is here, where we take a data attribute, which is by definition data, and we turn it into HTML, into code. And so if we take these XSS mitigations into account, let's assume this page has an XSS vulnerability. And we have XSS mitigations in place to defend against all the attacks, so it cannot be exploited. But now we have this XSS, and that's, oh, sorry, I forgot this. This is what we call a script gadget. This is legitimate functionality that is contained in the page and that upgrades a data text to an HTML. And now let's assume we have the XSS in the page. So we have an XSS here. So the attacker could insert a script, but that doesn't work because the XSS mitigation would block it. But now we can just insert a button, give it the same marker string, and then a data text. And into the data text, we just put our payload. And the payload is now just data. It's just a string. Any XSS mitigation would not block it. And interestingly, we can also encode it because the browser does some decoding steps when we read an attribute from the HTML. So in this case, we can simply inject this, and then the script gadget here in the page will see both buttons, and it will upgrade our button to execute script in the page. And all of this is legitimate markup. It's a div tag. It's a couple of data attributes. There are no scripts. There's no onload handler, and so on and so forth. And this is basically how a script gadget works. And to summarize, a script gadget is a legitimate piece of JavaScript in a page that takes a seemingly benign piece of HTML and upgrades it to code execution. And that's how we can bypass XSS mitigation. And here I quickly want to summarize the attacker model. So here we see how an XSS works. So we have the document object model. We have an XSS flaw in the page, and usually attackers inject HTML. Usually inject HTML into the DOM. But however, we have this XSS mitigation that prevents us from doing any malicious stuff. But now there is this script gadget in the page that takes non-malicious stuff and upgrades it to execute our payload. And that's how we can circumvent all the XSS mitigations. And we found this phenomenon in one or two examples. And then we were thinking, how widespread is this? How often do script gadgets exist in pages? Is this like an isolated issue, or is this like a bigger issue? So what we did is we did a quantitative manual analysis of popular JavaScript frameworks. And we wanted to answer two questions. First, we wanted to answer how common these gadgets are in modern JavaScript libraries, and how effective are they in bypassing XSS mitigations. So we compiled a list of 16 popular libraries. So we just went to GitHub, we searched for all the libraries that had the most stars and forks and so on, and compiled this list, and it contains things like Angular, Aurelia, Bootstrap, React, Closure Library, Polymer, so all the popular frameworks. And then we tried for each framework, we tried to find a mitigation bypass for one of 4 XSS mitigations. So we looked at XSS filters, at HTML sanitizers, at web application firewalls, and at the content security policy. And in the next maybe 20 minutes, I would like to go through all of these examples and give 1 or 2 examples for each of the mitigation techniques and try how you can bypass them. So let's start with the most simplest one, with WAFs and XSS filters. And WAFs and XSS filters, as I explained, they usually use rules or regular expressions to detect payloads. And I already showed how they can be bypassed, right? So we have legitimate code that gets upgraded. So basically, when we look for gadgets that bypass this, we basically look for legitimate pieces of code that get upgraded by a library. For example, where a legitimate attribute is passed to eval, or where a text node is passed to inner HTML, and so on and so forth. And here I have a couple of examples. I have this longer one example that I would like to present in details, and I have a couple of shorter ones just to see how widespread this is. So here we see a construct from the knockout library, and they have this concept of data bindings. So you have this data bind attribute, which has no semantic in HTML, it's just a data attribute. And then you can type in value, and then you can have any kind of data here. And what happens at runtime is that knockout basically, when it bootstraps, it says, give me all the elements that have this data bind attribute. And then it gets this attribute. And then what it does, it creates a data binding. So it creates a a function, and this string, this data value, goes into this function. And this function is called by the framework to update the value. So whenever you change the value, it will call the function will return the right value, then the framework will put it into the right place, into this diff element. And then after this function is created, it will just be called at runtime. So effectively what this creates is a chain from a attacker controllable value that is benign to a function call that is executed. So basically we have code execution here. And this means this data bind attribute behaves like eval. So you have this data bind attribute, you have the script gadget in the page, in the knockout library, and this is effectively just evaling this value. So in order to bypass an XSS mitigation or a web application firewall in this case, you can just say data bind value alert 1, and this will open an alert box in the application. And no XSS mitigation would be suspicious of this data bind attribute. Here are a couple of other examples. This is from the Bootstrap library, and the Bootstrap library has a tooltip functionality. So you can just say render a tooltip for me, and the library will take care of all the rendering and the effects of the tooltip and so on. So how you do that is you just put a marker attribute again on your element that you want to have the tooltip with, and then you have a title attribute. And this is what actually rendered in the tooltip. And interestingly, by default, this is just rendered as text because you don't need HTML in a tooltip usually. However, Bootstrap has this data API where you can just change internal configuration settings of Bootstrap by specifying a data attribute. So what you can just say is data minus HTML equals true. This will change the internal configuration value, and then this will be rendered as HTML. So and then we effectively bypass XSS mitigations again. Here's another example from the Dojo library. So here, I don't even really know what this does. This is just a declaration. I think you can declare some variables or configuration values. And interestingly, all of these properties or attributes are just thrown into eval with some other code around it. So you can simply break out here of the current context. You can just type alert 1, and you get an alert. It's very simple. And here's a summary of the findings for XSS filters and web application firewalls that we had. So we looked at 3 filters at Chrome, Edge, and NoScript. And for web application firewalls, we looked at mod security. And we found that in most cases, we were able to bypass 9 out of 16 cases. For Chrome, it was a bit higher because Chrome tries to prevent false positives. So all the other filters are trying to overcatch and catch as much as possible, but don't necessarily want to. So they catch more than what could actually be an attack. Okay, let's move on to the next XSS mitigation, HTML sanitizers. So as I said, HTML sanitizers work by just taking a string and removing all the HTML, the malicious HTML parts. And again, we can use script gadgets to circumvent HTML sanitizers because most of the sanitizers would leave script gadgets intact. And here are a couple of examples. And the first one was not part of the 16 popular libraries, but it's so weird that I wanted to show it anyways. And this is of a library called Ajaxify. And Ajaxify has a class, and this class is called document script. And if you put it anywhere, it magically turns the element into a script tag. So it will just take this value, it will create a new script tag, will write this to the script tag, and append the script tag to the DOM. So, and it's perfect because class elements are allowed by all the sanitizers that you can find out there. Another example we've already seen is the Bootstrap example again. So here it's exactly the same. We've seen that already, I explained it. It will just some sanitizers allow data attributes to pass through the sanitization, and usually title attributes are always left in place by all sanitizers. So in this case, this bypasses a couple of sanitizers. And we did a study on 2 sanitizers. We looked at DOM Purify and at Closure, and we were able to bypass DOM Purify in 9 of 16 cases and Closure in 6 of 16 cases. And we have a GitHub repository with all the exploits and proof of concepts. Okay, let's now go to the most interesting one, so to content security policy. I don't really have a lot of time to explain how the content security policy works. I assume that there's some basic knowledge, but basically there are 2 different modes I would like to look at. And there is a whitelisting mode and a non-space mode. And in the whitelisting mode, you whitelist origins that are trusted, and in the non-space mode, you put a nonce on every trusted script, and the nonce is generated at page load time and is not known by the attacker. So the attacker cannot inject the right nonce, and that's why the attacker cannot inject a legitimate script. And additionally, CSP has some keywords to make your life easier. So CSP is quite hard to deploy if you have an existing application, and that's why some keywords exist that relax CSP. There's unsafe inline, but that's insecure by default, so I will not talk about it. The second one is unsafe eval, and then there is strict dynamic. And first, I would like to talk about unsafe eval. So unsafe eval is interesting because for a long time people thought it's not very dangerous to put this into your policy, because usually you only have 1 or 2 places where you need to use eval in your application. So you could just audit those 2 places, and then you could put unsafe eval and securely use that. The problem again is with script gadgets. You might have a chain from the DOM into eval. And here's one example. So this is from the underscore templating library. And underscore has some syntactic sugar for developers so that you can write code faster. So instead of writing script alert 1, you would just write smaller than %, and then you can put your script. And then the underscore library, when it will automatically evaluate all templates that you have in a DOM with this type, so you can just have a div tag, and then will execute code for you. So in this way, you can bypass unsafe eval. And there are a lot more libraries that do these kind of things. The second keyword I would like to talk about is the strict dynamic keyword. So the strict dynamic keyword is a bit tricky, and it's mostly used in the nonce-based mode. So in the nonce-based mode, you need to have this nonce in every script. The problem is that a lot of scripts that you include are not aware of this fact. For example, you might include the Facebook like button as a script or some other widget, and this widget might not be aware that you are using a CSP in nonce-based mode. So they would not take the nonce and add it to the newly created scripts that these libraries create. And what strict dynamic does is that it allows trusted scripts to create new scripts without a nonce. So the idea is if you nonce the Facebook script can load other Facebook scripts without explicitly propagating trust. So if a legitimate script can basically add new scripts. And this is interesting because we can again see this in script gadgets. So here we have an example that bypasses strict dynamic, and this is from jQuery Mobile. And jQuery Mobile has a pop-up functionality. So you can just press a button and there will be this overlay pop-up. And when you do this for performance reason, they pre-render this pop-up. And when you click the button, it will just come to the front and not be hidden anymore. So they pre-render this, and I guess a lot of developers ask themselves, what is this div element? Where is this div element coming from in my page? So the jQuery Mobile developers added a comment into this div element and said, hey, this is the placeholder for the pop-up that you defined with the ID. So they just have this comment and print the ID. So in the ID, you can just break out of the HTML comment they use and add a script behind it. And interestingly, there is they use jQuery to render HTML. So they don't use the native inner HTML, but jQuery. And when you render HTML with jQuery, jQuery will parse your HTML, and then it will, instead of just inner HTMLing scripts, which would not work, they see, oh, there is a script, so they create a new script element for you, and then they append this new script element to the DOM so that it executes. So in this case, we have jQuery, which is in your page, which you probably trust, so it has a nonce, creating a new script and appending it to the page. And that's exactly bypassing strict dynamic, because you have a trusted script that does it for you. Okay, now let's come to the most interesting gadgets. So about the ones that bypass whitelisted nonce-based CSPs. So let's assume we have a CSP policy where we removed all those insecure keywords. We removed unsafe eval, unsafe inline, and strict dynamic. And we are super secure. Everything is great. These are the hardest policies to circumvent, but actually we managed this by using expression parsers. And before going into details about the exploits, I would first like to explain how expression parsers work. So in our study, we found 5 libraries that ship own expression parsers. So basically, they build a language on top of the framework, a domain-specific language that allows them to do like syntactic sugar for developers. And they do so without using eval. They are just interpreting the code. They basically ship interpreters. And I want to explain this with the expression language in Aurelia. So here we can see a very simple example. So if you can use an expression, you just start with these $ and then curly braces. And then you can just, for example, say things like customer.name. And this is an expression, it's not JavaScript, and it will be interpreted. And then the Aurelia framework will basically look, is there a customer object in my scope? If yes, it will return the custom object, and then it will print the name here for you. And the nice thing is usually you have two-way data bindings here. So once you update this name anywhere in your application, Aurelia will make sure that it also gets updated in your HTML. And that makes it very easy to write HTML. You don't need to write a lot of JavaScript code to update a value. So here you can see what happens inside Aurelia. So whenever they parse such an expression, they basically see that, okay, this is an access to a variable or to a function, and then they will just look this up. So they have a scope object. In this case, this is already the customer object, and then they just get this name, put it here, and then they return the property. However, with these expression languages, we can do more. So here is an example where we call a function. And this is not JavaScript. This gets interpreted by the framework, and it will basically look up the say hello function inside the framework scope, and then it will just call it without using eval. And here we see how that works. So it will look up this name, will get a function reference that it already has somewhere, and then it will apply some arguments and will just call this function. And that allows us basically to execute arbitrary code. And I would like to explain how that works. So here we have a very simple payload in the Aurelia framework that calls the alert function. So what we can do in Aurelia is we can just give an element a name, and we can use the s.bind, which is again an attribute without semantics in HTML. And then we can just say, okay, give me a reference to this element, to my local element. And then we have a reference, and we can say, okay, give me the owner document of this element, which is the document object. And the document object has a reference to the window object. And in JavaScript or the XSS world, whenever you have a reference to the window object, you basically won. It's like in the binary world, you want to control a certain pointer. In JavaScript, you want to get a reference to window. And then if we have a reference to window, we can just call the alert here. And that bypasses the mitigation because all of the JavaScript execution is happening in the Aurelia framework. That's in the page, that's legitimate code. And basically, we can do weird things with it. So for example, here, we have a cookie stealer that is completely JavaScript free. So usually when you learn about XSS, your first payload that you write is usually you have a document write, then you write an image tag, a URL, and then you do plus document cookie. That's the usual way. So here, this is the same, but just with expression languages. So instead of inserting a script that has this document write, you just insert this image with the URL, and then you just tell the Aurelia framework to fill the cookie in at the right place. So you just say here, okay, take the global object, which is window, then give the document, and then put the cookie. And there is no JavaScript involved. This is all like domain-specific language of Aurelia. And we can actually do a lot of crazy things. For example, let's assume now we have CSP in place, and CSP uses nonces to validate whether a script is legitimate or not. So we can, for example, use expression to just let the framework insert the nonce for us. So here we have an example. We have a script, and that the attacker injected, and at the injection time, we don't know the nonce, right? So we just add a nonce attribute, and in this nonce attribute, we specify an expression and say, hey, Aurelia framework, please insert the nonce for us here. And then the Aurelia framework will happily do that. And it will go to the document, it will say, what is the current script, which is the Aurelia script, and we'll just get the nonce from there and add it to this. So you have a valid script that bypasses the policy. Okay, so we looked at these 4 different modes. So we looked at the whitelist and nonce-based modes. We looked at unsafe inline and strict dynamic. And what we see here is that whitelists and nonces are pretty strong. We were only able to bypass in 3 of 16 cases or 4 of 16 cases. But whitelists have other problems. So we had a paper last year in CCS where we showed that they are basically insecure. So you shouldn't assume that whitelists are the safest solution in this case. But what we see is that like those unsafe keywords, they dramatically lower the protection capabilities of a CSP policy, especially the strict dynamic keyword. And when we envisioned the strict dynamic keyword in the beginning, it was called unsafe dynamic. And then someone in the standardization committees thought unsafe dynamic is really a bad word. It should really be called strict dynamic. And it was, I think, in hindsight, a very bad choice. Okay, so this was the study that we did on libraries. And basically, we were able, from the combination of libraries and XSS mitigations, we were able to bypass all the cases in 53% of all the cases. And However, we always stopped at the first exploit. So whenever we were able to bypass a mitigation technique, we stopped. So there might be multiple other bypasses and gadgets in the libraries that we didn't look at. And we found out that basically the expression-based ones are the most powerful ones, but they are quite effective in bypassing all the mitigation techniques that we've tested. As a next step, we conducted an empirical study, and we did that together with SAP and with Samuel Groß and Martin Johns, and we wanted to find out whether gadgets exist also in real-world pages. So now we looked at libraries, and these libraries are very generic. They have a lot of crazy code in there. They do a lot of automatic things. So maybe it's different when we look at developer-written code and not at this very generic library code. So we again had the same questions. We asked ourselves, how common are gadgets in real-world applications, and how common are they? How effective are they in bypassing XSS mitigations in real-world websites? So what we did is we built an engine that can detect gadgets and verify them. So how this works is that we have a taint tracking engine that we build into Chrome and Firefox. And with this engine, we crawl the Alexa top 5,000 websites. And these websites might contain a gadget here. And if a gadget is contained, we have a data flow from the DOM tree into a security sensitive function. So we patch the DOM and the security sensitive function. And basically what we get out is a data flow from the DOM to security sensitive function. We can then use this data flow to pass this to an exploit generator. And the exploit generator will generate a gadget-based exploit. So here we see it's a legitimate markup that contains in the data text attribute like our payload. And our payload contains a function here. And we then inject this gadget back into the page. And then we wait for a function call. And if we see this function call from for example, a data text attribute, we know that there was a code in the page that upgraded our data to code execution. And we ran this on the Alexa top 5,000, and we basically found gadget-related data flows in 82% of all the websites. And I assume the other 18% were offline or were just like some static pages that don't have JavaScript at all. And then we ran these 82% of the flows through our exploit generation engine, and we basically verified about 285,000 gadgets in the Alexa top 5,000. Those gadgets are not necessarily unique. There might be duplicates because you use the same library across many different pages. So we looked at the domains, and we verified gadgets in about 20% or 906 domains. However, our detection and verification approach was very, very conservative. So we didn't want to have false positives. So we bought a 0 false positive rate by accepting a large number of false negatives. And we actually looked at a lot of flows manually. I looked at about 100, and most of the flows were exploitable. So my assumption is that we are somewhere between 20% and 82% of the websites that have gadgets. And from my gut feeling, I think we are rather at the 80% and not at the 20%. As a next step, we looked at how effective gadgets would be in bypassing XSS mitigations. And this was kind of tricky because most of the websites don't have these mitigations, and we cannot just deploy them onto the web applications because we would break the applications. We could also not say if there's a web application firewall, for example, because it's hidden and so on. So these are just theoretical numbers where we looked at the number of data flows. We didn't actually try to exploit things. And we first looked at HTML sanitizers. And for example, what we saw is that 60% of all websites contain a data flow from a data attribute to a security sensitive function. And by default, most sanitizers allow data attributes. So we believe that in most cases, sanitizers can be circumvented. As a second step, we then looked at XSS filters and WAFs and CSP unsafe eval, and we just wanted to know how many eval-based data flows there are in websites. And about every second website has a data flow from the DOM into eval. And last but not least, we looked at CSP strict dynamic, where trusted scripts create other scripts. And we found that about 73% of all the sites have a data flow that results in a script tag being appended to the DOM by a legitimate script, which is a pretty large number and which surprised us. And this is mainly due to jQuery because they have this weird behavior of parsing text and then appending scripts. Okay, so we did these two studies, and what we see here is that these script gadgets are everywhere. They are in all modern libraries, they are in almost all applications. And so we thought, what can we do about it? So we have these gadgets, and XSS mitigation don't seem to work. And so we asked ourselves, what are the root causes for XSS? And when we look at technology, we see that vulnerabilities are technology dependent. So we already had this case today So for example, if you use parameterized queries, you don't have SQL injection. If you use memory safe languages, you don't have buffer overflows and memory corruption bugs. And the same is true for XSS. And the problem with XSS itself is that XSS is core to the web platform, right? We use HTTP and HTML. So we create a big string on the server side. We send this string to the browser. Then we execute the string as code. Then at runtime, we create new strings. We pass those to inner HTML and eval. And everything in the web is string-based. And that is actually the reason why we have XSS in the web. And we have to say that XSS is extremely easy to introduce. It's extremely hard to find in an application. And it's one of the most severe client-side vulnerabilities that we have. And the root cause is how the web platform works. And if you think about it, we haven't changed the web platform in 25 years. So the DOM APIs that we use are still the same that we introduced 20 years ago in the 90s, and so on and so forth. And we're trying to dance around the problem of XSS and try to create all these mitigations and layers on top, but we're never tackling the root cause. And I think we cannot tackle the root cause for all of XSS, but we're trying to do that for DOM XSS, because we can probably not change the HTTP protocol to not use strings anymore. That would be too crazy. But we can solve subsets of the problem. And how we want to do that is that we are trying to we want to create a type system for the DOM. So right now, the DOM is based on strings. And here's an intent to ship. So we already have a first version in Chrome Canary. And what we are trying to do here is we are trying to replace all the string-based APIs that we have in browsers, inner HTML, eval, document write, script.source, and so on. And we will replace these with typed APIs. And these typed APIs will not accept strings, but types. For example, a trusted HTML type, a trusted script type, a trusted URL type. And the only way you can create such a type is through secure means. So you can either use a secure builder, or you can use a sanitizer, or other secure ways of creating those types. And by doing that, we get guarantees. A developer cannot introduce XSS into an application because all the ways he can get this type is safe. And if you only allow this assigning of types, then your application is safe as well. You don't even need to look at the application anymore. And here's a very simple example. For example, here we have a DOM element that's called foo, and we create a trusted type. And we create it, for example, by sanitization. And then we assign this to inner HTML. And that would be fine because we have a type, we assign it to inner HTML. And now we will have an enforcement mode that throws an exception whenever you try to assign a string to inner HTML. So you assign a string here, that would just throw an exception and would not be accepted. And that's how we can kill DOM XSS. However, we have a couple of huge challenges, and they are mainly not in the security part, but more in the usability part. So I think we can create a perfect system that is perfectly secure, and no one would use it. Or we can use the perfect system that everyone would use, but that is not secure. And that's where we are trying to, right now, working on getting the right balance. So we have two big problems. The first one is backwards compatibility. So how do we deal with older browsers that don't support these types? And I think we have a good story there. We have a polyfill that basically creates these types in other browsers. So today you could use trusted types in your applications if you want. And we are actually using them in a lot of applications. And I think GitHub is using them as well. And Facebook is also using similar concepts, type-based systems to prevent XSS. And they are pretty successful in doing so. But the much larger problem that we are currently tackling are unsafe conversions. And, I need to hurry a bit. Yes. Oh, shit, I'm late. Are unsafe conversions. So we have a lot of applications that require some form of unsafe conversions, where you have a seemingly untrusted script, but out of the context, this is secure in this context. So please make it secure. And we are currently thinking about different ways to enable these unsafe conversions. And here's a call to arms. If you're a JavaScript developer, if you're developing JavaScript libraries, or if you're just interested in working on an exciting new web platform feature, then just reach out to us via Twitter, via email, or just today, and try to help. Okay, with this, I would like to summarize and conclude. So what I showed you today is that XSS mitigations work by blocking attacks and not by preventing the bugs. However, we see that so-called script gadgets can be used to circumvent mitigations. And script gadgets are legitimate pieces of JavaScript code in an application that upgrade a legitimate HTML to script execution. And what we saw is that script gadgets are prevalent in all libraries and all applications out there, and they are very effective in bypassing all the XSS mitigations. And what we see is that the web platform hasn't changed in about 25 years, and we think that in order to address this problem, we need to change the root, or we need to eradicate the root cause and make the web platform secure by default, so that developers just cannot introduce bugs, because trainings and guidelines are nice, but they often don't prevent your developers from accidentally screwing up. And in order to do so, we introduced this new type system that we want to build into browsers, and we are still discussing with browser vendors and other people to get this into other browsers as well. But the idea is that when we get this in everywhere and when developers use the system, we can basically fight one full class of vulnerabilities. This, I would like to thank you for your attention, and I don't think we have time for questions, but
thank you, Sebastian.
Thank you.
One urgent quick question. Recording. Okay.
I think it's very interesting what you said. But as far as I understood, you didn't mention Angular 2 and Angular 4 and so on, right?
Yes.
And for instance, Angular 4 is TypeScript, right? So
yes.
The methodology you are proposing to fix the problem is kind of the same that they already use.
Yes, Angular is using that concept already, right? But I think it should be in the platform. It should not be limited to big frameworks, because we see a lot of crappy frameworks that cannot afford a team of developers implementing I don't know, their own template compilers and so on. So I think that should be a platform feature. But yeah, we also didn't look at Angular 2 because at the time we started this, Angular 2 was pretty new. And so we looked at Angular 1 only.
Okay. As the time, he's here all day, so I think the next break you will be very busy. Thank you, Sebastian.